Characteristics of a coil and a capacitor. A generator G delivering an alternating sinusoidal voltage given as UAM equals UG. So UAM between point A and point M is the same as U of G. It's given as UM, the maximum or the amplitude of the voltage multiplied by cosine omega t. A coil of inductance L, this is the coil, and internal resistance R. And we have two resistors, R1 and R2. R1 is given as 10 ohms and R2 is given as 32 ohms. We have an oscilloscope connected and conducting wires. The first experiment, or the aim of this experiment, is to determine the inductance L, the internal resistance R, and the capacitance C. Experiment 1, we set up the circuit of document 1, this circuit. The circuit thus carries an alternating sinusoidal current I. The oscilloscope, conveniently connected, allows us to display the voltage UAM across the channel Y1 and UBM across the channel Y2. We obtain the waveforms that are shown in document 2. First part, we have the sensitivity there. First part, redraw the circuit of document 1 and show on it the connections of the oscilloscope. So we have to show the connections of the oscilloscope. Okay, we have UAM and UBM. UAM on channel 1, so I'll write it. They mentioned that we represent UAM, which is the same as UG on channel Y1. And we have UBM, which is the voltage across R1. We represent it on channel 2. We have M in common, so first thing we take M as the grounding. Then UAM should be between A and M. Let's change the coloring. Okay, so for UAM, I will connect Y1 at this point. And for UBM, it's between B and M, so I'll connect the channel 2 at this point. So channel 2 we connected at this point. This for the first part, drawing the connections of the oscilloscope. The waveform A represents UAM justified. First of all, this is an RL circuit where the resistance and the coil are connected in series. Okay, in this case, since we have this case, then we will say that all the reasons together, we can say that UG leads the current I. Okay, and since curve A, if you check, this is curve A, it's before, or it reaches 0 before curve B. So since curve A leads curve B, then we will say that curve A represents UAM. Okay, so UG is the same as UAM, it leads I. So curve A leads curve B from the figure, then the leading one, curve A, represents UG, and curve B represents I. Will see this in another part. Referring to document 2, determine the angular frequency of the voltage UAM. Okay, the angular frequency, which is omega, is equal to 2 pi over t. So first thing we have to find t. T is not given. T is equal to, let's count, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 divisions multiplied by the the sensitivity for this one is 2.5 milliseconds. So 8 times 2.5, we will get 20 milliseconds. If we convert to seconds, it will be 20 times 10 to the power of negative 3 seconds, or we can write it as 0.02 seconds. Now to find the frequency, the angular frequency, we will do this. We'll use this formula. Omega equals 2 pi over t. So it is equal to 2 pi over 0.02, and this results in 100 pi. The unit is radians per second. Now, find the amplitudes UM and UM1 of the voltages UAM and UBM. We said that UAM is on curve A. So let's label the curves. So this one is UAM and this one is UBM. Okay. To find the voltage UAM, let's start with UM. That is, UM is related to UAM, and I will use a different color to differentiate. We can say that UM1 relates to UBM. Okay. Now, UM is equal to the sensitivity, the vertical sensitivity for curve 1 multiplied by how many divisions we have vertical. So UM is equal to UM, I chose UAM for this one. So I have 1, 2, I zoomed it in to see the divisions. 1, 2. So we have 2 divisions multiplied by the sensitivity was 5 volts per division, and we get 10 volts. This is for UM, which is related to UAM or UG. Now, for UM1, which is related to UBM, which is the voltage across R1. So it is the sensitivity, the vertical sensitivity, the second vertical sensitivity multiplied by Y2, which is the number of divisions. So UM1 is equal to, we have 1, 2, and this one, if you take it on a scale, you will get 0.8. So it is 2.8 multiplied by the sensitivity was 0.5, and we get 1.4 volts. This is for the calculations of UM and UM1. For the phase difference. Okay. This is the first curve, curve A, representing UG, and this is the second curve, curve B, representing U across R1, or UAM and UBM. As you see, the difference between them is 1 division. Now, when we calculated the period, we noticed that 1 period corresponds to 8 divisions. So I will say now 2 pi corresponds to 8 divisions. The phase difference is from this point to this point, which is 1 division, will give me the phase difference. So we will get that the phase difference is equal to 2 pi multiplied by 1 division over 8 divisions. This results in getting the phase difference as pi over 4 radians. We can directly, by the way, calculate the phase difference. I will use another color to write the formula. We can say that phi, the phase difference, is equal to 2 pi multiplied by the number of divisions over the number of divisions per period. Okay. Or we can also write it as equals 2 pi d over d, where d is the number of divisions for phase difference, of course, and d is the number of divisions for one period. Write down the expression of the voltage UBM as a function of time. First thing, UBM, we mentioned that it is the voltage across R1. So it is equal to I R1. It is the same current in the circuit since it is a series circuit. Okay. So UBM is equal to UM1, the maximum voltage related to UBM we calculated before, multiplied by cosine of omega, which is 100 pi t, minus the phase difference, which is pi over 4. Or we can write it, we replace UM1 by its value, which was 1.4. So UBM is equal to 1.4 cosine of 100 pi t minus pi over 4. Where UBM is in volts and T is in seconds. Deduce the expression of the current I as a function of time. Okay, again, UBM, which is U across R1, is equal to I R1. So I is equal to UBM over R1. We found UBM in the previous part as 1.4 cosine 100 pi t minus pi over 4 over R1 is 10 ohms. So we get I in the form of 0.14 cosine of 100 pi t minus pi over 4. This is the formula for the current I. Determine the values of L. So we have to calculate the inductance L and R, the internal resistance of the coil, by applying the law of addition. So they specified that we have to use the law of addition of voltages, and they gave a hint where you have to use two particular or critical values for the time t. So first of all, UAM between this point and this point, UAM, which is the voltage across the generator, is equal to, or is distributed over the coil R2 and R1. So I can say that UAM is equal to this part, which is UAD between A and D, which is for the coil, UAD, plus the part between D and B, which is the voltage across R2, which, so I will write plus UDB plus UBM, which is across R1, the one we dealt with before. So this is UAD, this one is UDB, and this one is UBM. So UAM is UM cosine omega t of the generator equals UAD, which is for the coil. I will use a different color to differentiate between different parts. So for the coil, it will be Ri plus L di by dt. Why? Because we have an internal resistance and we have an inductance. Okay. Plus. Okay. So plus UDB, which is R2I, and UBM, which is R1I. So let's see how it's going to change. I will rewrite the formula now with one modification only. I will say this is UM cosine omega t equals Ri, which is R is an unknown, I is we found it as 0.14 cosine of 100 pi t minus pi over 4. This was for I, plus L is also an unknown, d by dt of I, and I, as we said, it has a value which is 0.14 cosine of 100 pi t minus pi over 4. We close the bracket again. Okay, so it's like this. Now, plus I is the same for all. So it's R1 plus R2. Since they are in series, I can write them like this. R1 plus R2 into I, which is 0.14 cosine of 100 pi t minus pi over 4. Now, let's continue. I will take critical points or critical values or particular values for t. How do I choose them? I have to make sure that the values that I choose will simplify the equation. So let's see what I mean. For example, if I take omega t, isn't this like omega t? Okay. If I take omega t, so instead of 100 pi t, I take it as pi over 4, it will become cosine 0. Let me show you what I mean. So first I will say, assume that omega t is equal to pi over 4, or we can write it as t equals pi over 4 omega. Let's replace in the formula. We will get the following. Okay. We will get um cosine pi over 4 equals r into 0.14 cosine of, instead of 100 pi t, it will become pi over 4 minus pi over 4 plus, now for LDI by dt, I will do the derivation, the derivative part, to take out the final form. So I will put it in yellow, golden yellow. Okay, so it will be, after L, it will be minus 14 sine of 100 pi t minus pi over 4. Okay, so we'll get back to the main color. So this was L. Okay, and I will replace this by pi over 4. Okay. So let's change to this. Okay. So this is L. we have I di by dt is this shape, this form. Now R1 plus R2, okay, R1 plus R2, we had R1, it was given as 10 ohms, and R2 was 32 ohms. I will write them. R1 is 10 ohms and R2 is 32 ohms. So, plus, we are there now. 10 plus 32 into, we write this 0.14 cosine of pi over 4 minus pi over 4. Instead of omega t, I replace by pi over 4. Or instead of t, I replace pi over 4 omega. Now, we found it as 5. I will replace with a different color for the cosine and sine functions. So was 5. Okay. Cosine, we'll use that. Cosine pi over 4 is radical 2 over 2. Sorry, we have to fix this. I checked it, it was 10. So this one is not 5, it's 10. Let's change it. Okay. So we had 10 multiplied by cosine pi over 4 is radical 2 over 2 equals R. Now, pi over 4 minus pi over 4, they cross out each other, so it will be like cosine of 0, which is 1. So R into 0.14 plus L is still there as an unknown. Now, we have sine pi over 4 minus pi over 4, so it's like sine of 0, which is equal to 0, then L into 0. Now, plus 10 plus 32 is 42. 0.14 cosine pi over 4 minus pi over 4. So this one with this one, they cross out, and we will get cosine 0 again, which is equal to 1. So into 0.14. Okay. Rearranging the formula, we will get that R is equal to 8.5 ohms. Now we have to calculate L. How do we calculate L? So to calculate L, I will take another value for the time, and I will assume this time that I will take that omega t is equal to 0. I will replace this in this start equation. Okay, so I will have cosine, instead of omega t I put 0, equals R, we found it as 8.5. I'm working on this equation. 8.5 multiplied by 0.14 cosine of 0 minus pi over 4 plus, now instead of using L di by dt, this one I will just replace in this one. So I will say it will be L into minus 14 sine of 0 minus pi over 4. So instead of omega t, whatever we have omega t, I replace it by 0 now on this part, plus 42 into 0.14 cosine. Now instead of pi over 4 or omega t, I will put 0 minus pi over 4, so cosine of minus pi over 4. Now, replacing the values of um, which is 10, cosine 0 gives 10, because cosine 0 is 1, is equal to 8.5 times 0.14 radical 2 over 2. So I will write it 8.5 into 0.14. Cosine minus pi over 4 is the same as cosine pi over 4, so it is radical 2 over 2 plus L is an unknown, I'm working on this one now, into minus 14. Sine of minus pi over 4, it gives minus radical 2 over 2 plus 42 into 0.14. Cosine of minus pi over 4 is radical 2 over 2. Minus and minus, it becomes plus, so nothing changes there. We replace and we get the final answer for L as 0.16 hundredths. Okay, the capacitor, we changed the combination now. The capacitor is connected in series with the electric components of the circuit, document 1. So we added this capacitor to the connection. The oscilloscope conveniently connected allows us to display the voltage UAM. As we said before, UAM is the voltage across the generator G on channel 1. Okay, so this is channel 1 is this one, and this one will be channel 2. Okay, and the voltage UBM, if we check, we will see that UBM is between this point and this point, so it is the voltage across R1. The obtained waveforms are represented on document 4. Before we solve for anything, as you see, they are in phase. There's no phase difference between the two waveforms. So I will say that, let's see the question. The circuit is the seat of current resonance. Justify. First reason, because we have both UG and UR1 are in phase, where UR1 is the image of the current I. So this is the answer. The circuit is the seat of current resonance, as we said. They are in phase. This is the first component or the first reasoning. The second point is that UR1 is the image of I. In case of current resonance, the angular frequency omega of the generator is equal to the proper angular frequency of the circuit. So omega, which is for the generator, is equal to omega naught or omega 0, which is for the whole circuit. This is called the omega 0 is called the proper frequency or proper angular frequency. Choose from the statements below the one that describes the correct that describes correctly the proper angular frequency of the circuit in this document. First, to avoid misconceptions, we know that they are in phase, but this does not mean that we are getting that or the exact description. So, statement 1. The proper angular frequency of the circuit is the angular frequency of UG. We said that they are the same, so till now it's correct. Such that the current I and the voltage U across the coil are in phase. Yes, they are in phase, so this is possible. We will see. 2. The proper angular frequency of the circuit is the angular frequency of UG. This is correct. So the proper frequency is the angular frequency of UG, such as the amplitude Im of the circuit I attains its maximum value. If you check UR1, it goes to its maximum value. So this is also correct. And by the way, once we say that the proper angular frequency is the angular frequency of the generator, then we're satisfying the condition that omega equals omega 0 and that they are in phase. Statement 3, the proper angular frequency of the circuit is the angular frequency of UG, the same thing. such that the amplitude of the voltage across the coil attains the maximum value. No, this is not necessarily true, because we're depending now on the current. The voltage is imaging the current, or is an image of the current, but our focus is to attain the maximum current. So the answer is statement 2. Write the relation among L, C, omega node, and calculate C. So I have to write the relation between the inductance, the capacitance, and the proper frequency, and then calculate the capacitance. Okay, we have mentioned that we have the state of, or the case of, current resonance. For the state of current resonance, or the case of current resonance, we can say that the angular frequency of the generator is equal to the proper frequency, as we said, and we found it to be 100 pi radians per second. This is the first thing. Okay, so omega, the proper frequency, is equal to the frequency of the generator, and we found that the frequency of the generator was 100 pi from the previous part. Now, also for current resonance, we can say that LC omega 0 squared is equal to 1. Okay, we found L is 0.16 henries, C is an unknown, and omega 0 is 100 pi squared equals 1. Calculating C, we will get 6.33 times 10 to the power of -5 farads.